Hi everyone. In this video, we'll be introducing a generalization of the Riemann integral called the Riemann-Stieltjes integral. Now, our motivation for studying this begins by thinking about the Riemann integral itself. So imagine we have a function, and let's say we're just going to look at a function defined on the interval 0, 1, and perhaps our function looks like this. And of course, we know that if I look at the area under this curve, right, this can be represented as the Riemann integral from 0 to 1 of f of x dx. Now, another way we can think about representing this area is the following. Imagine that we were to pull a number between 0 and 1 at random, okay? And we were then to plug that value in to the function f and see what we get out. Okay, so we might pull out pi over 4, right? That's sitting somewhere inside here. Pull out pi over 4, plug it into the function, see what I get. And then I pull out another number out at random. I pull out 1/2 and see what I get. And I repeat that over and over and over again. And I could sort of ask, in the long run, I wonder what the average value of the values I would get out of the function is. Okay. Now, you can formalize this in probability theory by talking about a random variable x, which is drawn from 0, 1. You would need to have some distribution there. But the idea is, if I think about this value x just being drawn sort of uniformly from the interval 0, 1, then this, in fact, is the average value that I will get out of that I expect to get out of that function. So by drawing x's at random, plugging them into the function, so the average that I expect, this would be the expected value of f of the random variable x, is actually just equal to this, if I assume that all points are equally likely to be pulled. Okay. But what if they weren't? So what if there was not a uniform sort of distribution of the probability across this interval? Well, in that case, that would change our probability, right? We would need to somehow think about weighting certain portions of the x-axis slightly differently. That's exactly what we want to do with the Riemann-Stieltjes integral that we're going to develop. We want to be able to think about taking this interval and having a non-uniform distribution on the x-axis. Now, the way we're going to think about this is we're going to think of this as changing what we're integrating with respect to. So instead of thinking about integrating with respect to x, we're going to think about integration with respect to a function. And we're going to call that function alpha in our particular case. Okay, so what we want to do is we want to try to generalize this notion of a Riemann integral to something else. Now, it's going to actually turn out that the Riemann integral itself is going to be a special case of this new Riemann-Stieltjes integral that we want to develop. But you can almost think of all of this as just sort of non-uniformly stretching and compressing this x-axis and then integrating in a slightly different way. So again, we'll see how that's going to work through all the definitions that we're going to develop. Okay. So now our next step is going to be to define the Riemann-Stieltjes integral. And if you think back to the Riemann integral and how we did that, we started with some sums. So for the Riemann integral, we started with Riemann sums and upper and lower Darboux sums. And then we use the upper and lower Darboux sums to develop the upper and lower Riemann integrals. Once we had the upper and lower Riemann integrals, we could then define what it meant for a function to be Riemann integrable, namely that the upper and lower Riemann integrals were equal. Well, essentially, we're going to do all of that same stuff now, but for Riemann-Stieltjes integration. And so we're going to take every definition and basically add a Stieltjes to the end of it. So instead of a Riemann sum, we're going to have a Riemann Stieltjes sum. Instead of a Darboux sum, we're going to have a Darboux Stieltjes sum. Instead of a upper and lower Riemann integral, we're going to have an upper and lower Riemann Stieltjes integral. And then finally, instead of a Riemann integral, we're going to have a Riemann Stieltjes integral. And it's actually going to turn out that our definitions are only going to change in one very small way. So to sort of see how that's going to happen, let's start with our first definition, the definition of the Riemann-Stieltjes sum. So suppose alpha. So alpha is going to be this thing that we're integrating with respect to now, right? We're not integrating with respect to a variable x. We're integrating with respect to this function alpha, which is itself a function of x. This alpha is describing sort of how we're non-uniformly changing that x-axis. So suppose alpha is monotonically increasing on the closed interval AB, and f is a function from AB into R and is bounded. So again, notice f is basically remaining unchanged. The conditions on f, we're just now introducing this monotonically increasing function alpha. If I let P be a tagged partition, and I set delta alpha k, so instead of delta xk from before, now I have delta alpha k, I want that to be alpha of x sub k minus alpha of x sub k minus 1. Okay, so again, instead of, if you come back to when we had a Riemann sum, here you had a delta xk. Now we're going to have a delta alpha k. Okay, so we define the Riemann Stieltjes sum of f with respect to alpha as this sum, where again, this looks just like the Riemann sum, except I've changed the delta x sub k to a delta alpha k. Now, let's back up to this delta alpha k. So what is this doing? Instead of the delta xk, which just measured the length of that interval, I'm now transforming, non-uniformly possibly, the x values. And so I'm going to transform the x values by alpha first, and then look at their difference. So one way to think about this is these rectangles areas, right? I'm still using the function value to give me the height of the rectangle, but now the base of the rectangle isn't necessarily just the width of that subinterval of the partition. You take those points of the partition, you transform them by alpha, and then you look at the difference there to give you, of the transformed partition values, to give you the width of the rectangle you're using to approximate. So x sub k minus 1 and x sub k could be very close together, but once you transform by alpha, they could be further apart. And now you're sort of weighting that function value a bit more because you're transforming the length of that partition. Okay, so again, from like just writing down the definition, the only thing that's changing is this delta alpha k bit. All the delta x sub k stuff has been changed to delta alpha k. The other thing I want to point out with the delta alpha k's is they must be greater than or equal to 0 because alpha is monotonically increasing, right? So to be an increasing function, right, increasing means that if x is greater than y, then alpha of x is greater than or equal to alpha of y. Okay, so because this alpha is increasing, and my x sub k values, these form a partition. So since these form a partition, x sub k must be larger than x sub k minus 1, strictly larger. However, once I transform them by alpha, this could be 0, right? So technically a constant function is considered increasing under this definition, which is the standard definition of increasing. Okay, so I know that I can't say that the delta alpha k's are, I can't necessarily say that the delta alpha k's are all strictly positive. I could say that about the delta x sub k's, but I can't say that about the delta alpha k's. But I do know that they're non-negative. They're greater than or equal to 0, which is really still enough to do what I need to do. Now, the sort of running joke with the rest of this is all the other definitions are going to change in exactly the same way. we're going to replace delta x sub k's with delta alpha k's, because the whole point of this integral is just to weight values on the x-axis slightly differently. So instead of having delta x k's weighting things, we need delta alpha k's weighting things. So we can also change our definition of upper and lower Darboux sums to get upper and lower Darboux-Stieltjes sums. So again, if I let capital M sub k, this is still going to be the supremum of my function over the interval x sub k minus 1 to x sub k. So that doesn't change. We're not changing anything about how we calculate heights of rectangles. Those are remaining unchanged. Okay, so for upper sum, I'm going to use this capital M sub k, which is the supremum of the function over that subinterval of the partition. The little m sub k is the infimum of the function over that subinterval of the partition. But then when I go to define upper and lower Darboux sums, now I'm going to have u of pf alpha is equal to the sum k equals 1 to infinity of capital M sub k times not delta x sub k, now it's delta alpha k. Okay, same thing for the lower Darboux-Stieltjes sum. I'm going to have the sum the sum k equals 1 to infinity of little m sub k times delta alpha k. So again, everywhere I'm just changing how I weight these function values, right? So the heights of the rectangles are staying the same. I'm just changing how I weight those heights by transforming my partition values. All right. Once I have this, I can now define a upper and lower Riemann-Stieltjes integral, again, in exactly the same way. So if alpha is monotonically increasing and f is bounded, then I can define an upper and lower Riemann-Stieltjes integral. It's just going to be, the upper integral is going to be the infimum over all partitions of the upper Darboux-Stieltjes sums. The lower Riemann-Stieltjes integral is simply going to be the supremum over all partitions of all the lower Darboux-Stieltjes sums. So again, you're just adding a dash Stieltjes on the name of everything, and you're just changing every definition to have delta alpha k's instead of delta x sub k's. But fundamentally, it's all exactly the same idea, right? So here, the upper Riemann-Stieltjes integral, you can calculate all these upper Darboux-Stieltjes sums, and you know that each of these, it's this set of values, because each Darboux-Stieltjes sum is just some number. So this is a set of real numbers. It is bounded above, and it's bounded above and bounded below, as a matter of fact. So it's bounded. It's a bounded non-empty set of real numbers. The infimum must exist. The supremum must exist. Okay, so both of these values, the upper and lower Riemann-Stieltjes integral, always exist, just as the upper and lower Riemann integrals always existed. And then finally, we just say that a bounded function f is Riemann-Stieltjes integrable with respect to alpha if and only if the upper and lower integrals are equal, right? So and in that case, we would write then that the integral from a to b of f of x d alpha x, or equivalently, sometimes we drop the of x bits, so we might just write the integral from a to b of f d alpha, would just be equal in that case to, say, the upper Riemann-Stieltjes integral. You could also write the lower Riemann-Stieltjes integral, because we're talking about the case where they are equal to each other. If they're equal to each other, we're just saying that the value of the Riemann-Stieltjes integral is just that common value of the upper and lower Riemann-Stieltjes integral. Okay. Now, let me point out a couple of things as we look at these definitions. So if I just back up to the first one, imagine we pick our function alpha. Imagine we pick alpha of x to be x. Well, then that function is monotonically increasing, so that's a valid choice for alpha. If we do that, then what happens? Well, then down here, our delta alpha k's, that's defined to be alpha of x sub k minus alpha of x sub k minus 1. But alpha of x is just x, so this is just x sub k minus x sub k minus 1, that's actually just delta x sub k. So if we fix alpha of x to just be x, then our Riemann-Stieltjes sum just becomes a Riemann sum. Our upper and lower Darboux sums, well, that'll just become delta xk, that'll become delta xk. They just become our upper and lower Darboux-Stieltjes sums become upper and lower Darboux sums. And therefore over here, again, these are then just upper and lower Darboux sums. So this just becomes an upper and lower Riemann integral. And this just becomes the Riemann integral. So what we see is that this Riemann-Stieltjes integral, in the special case where alpha of x is equal to x, it's just the Riemann integral. But we can look at lots of different kinds of alphas and see that what we recover is actually some other thing, right? Some other object. And we'll actually look at least one, we'll look at one example in this video and more examples as we progress in talking about the Riemann-Stieltjes integral. So again, the whole point of the Riemann-Stieltjes integral is to generalize the Riemann integral. And what we're seeing here is indeed that the Riemann integral is a special case of the Riemann-Stieltjes integral where alpha of x is simply taken to be the identity function, taken to be alpha of x is equal to x. All right. Now, the next thing I'd like to do is just show a brief visualization to help us sort of maybe gain a little bit of geometric intuition about what the Riemann-Stieltjes integral is actually doing. So in order to do that, I've created a demonstration in Desmos that we'll walk through to just help us visualize a bit of what's going on. All right, so here we are in Desmos. And what I hope you can see here is that there is a function plotted in blue here. This is actually just like a cubic that's been shifted and distorted slightly. So this is just some cubic function f, and I want to imagine that I want to calculate the Riemann-Stieltjes integral of this function. Okay. Now I'm going to integrate it with respect to the function alpha of x is equal to arctangent of x. So we'll actually see the graph in a second, but it is monotonically increasing. This is something that makes sense to do. But it's less than the specific functions. I just want you to see geometrically how we can think about these things. So if I first have here, my function that I want to integrate. And if I were to draw this function alpha of x, and let me just first draw it here in the xy plane. So I currently have the function f of x, and there's reasons for this. I have my function f of x is plotted in the yz plane, and I'm plotting my alpha of x in the xy plane. So what I want to imagine you do is you take both of these functions. I'm going to take my function f of x, and I'm going to sort of expand it across the in the x direction. I'm sorry, I should say, let me back up. The function f of x, the function f is plotted in the xz plane, not the yz plane. So I'm going to stretch this in the y direction. Okay, I'm going to take this function. I'm just going to sort of, pull that function out in the y direction. I'm also going to take my function alpha of x. So again, it lies in the xy plane, and I'm going to pull it up in the x direction. So if I do that, and just sort of turn that on, I'll have that purple, this purple curve here. Okay. So you can imagine that there's sort of an intersection here. And what I want to do is I want to look at the portion of the purple function which is below the blue surface, but above the xy plane, Okay, so if I sort of take that, really what you can imagine is where we had that red curve before, I'm just going to sort of pull that up, but keep it under here. Okay. Now, if I look at this, and I'm just going to turn the purple off there for a second. So if I look at this just straight down the y-axis, if I think about in this plane calculating the red area there, that's actually the Riemann integral of f dx. Okay, so I've sort of taken the alpha piece out of it because I'm looking, right, this alpha function lives in the y plane, but I'm looking straight down the y-axis, so I'm not even really seeing that function. Really, all I'm seeing here, that red area would be the Riemann integral of f. In this case, I'm going from -3 to 3. So I'm looking at this function from -3 to 3, and that would give me the Riemann integral of f under there. But now let's imagine I take and I turn this so that I'm looking at this down the x-axis. Now, if you think about sort of what's happening here, when I was looking on the y-axis, if I had had a partition of x values, I'd still be looking at that partition of x values, right? Because I can see the whole x-axis. But now if I look down the x-axis, what happens is, and let me just sort of put it at an angle here so you can see. So what I'm doing now is, instead of looking at the partition of x's, I'm looking at the partition of y's, but y's are my x's that have been transformed by alpha. Okay. So when I look here, straight down the x-axis, what I'm seeing is an area where all the x values have been transformed by alpha. So all those little partition values of x have been changed to alpha of x. And so now I'm looking at sort of the same area. Well, it's a different number for the area, but I'm looking at the same region, but I've transformed it by this alpha. And now the area of this red region would be the Riemann-Stieltjes integral of f with respect to this function alpha, which in this case is arctangent, right? And if you think about the arctangent function, it's pretty flat as you get away from the origin. So what's happening, if I sort of go back here, is as I get out here, essentially what is happening is it's sort of smushing things in that are further away, right? X values that are further away, they're all getting smushed in. And so, for example, this peak, when I transform it over here, is going to become much more dramatic because everything is being sort of squashed together that's further out, right? And everything that was near the origin is staying a little closer to normal. So again, you just notice that this peak gets a little more prominent, a little steeper, as does this drop off here. So again, if I just go back over here, again, we'll just see, right? This drop off is now steeper. This peak is more prominent just because of the way that this particular alpha behaves. Of course, if you chose a different alpha, things would be different. You would get a different looking region. But this just gives you one example of geometrically what's going on with the Riemann-Stieltjes integral. So now that we have a better sort of geometric understanding of what's going on, let's see if we can understand this through working through an example. So imagine that I have a function f of x. I'm just going to take this function to be x cubed plus 1, and let alpha of x be the indicator function of the interval 0 to infinity. So if you prefer, we could actually think of this as just being defined as the function, right, which is 1 if x is greater than or equal to 0, and 0 if x is less than 0. And the question we want to ask ourselves is f Riemann-Stieltjes integrable with respect to this alpha on the closed interval -1 to 1? So everything we have to work with right now are just definitions. Okay, so if we want to know whether the function f is Riemann-Stieltjes integrable with respect to alpha, then we've got to calculate the upper Riemann-Stieltjes integral and the lower Riemann-Stieltjes integral. In order to do that, we've got to calculate some upper and lower Darboux-Stieltjes sums. Okay, so let's start there. So what I want to think about first, right, is what does one of these sums look like? So if I have some partition P, what does the upper Darboux-Stieltjes sum of f with respect to alpha look like over that partition P? Well, right, by definition, this is the sum k equals 1 to n of capital M sub k times delta alpha k. Okay. Now, the first thing I want to do, I want to focus on what do these delta alpha k's look like. So let's actually think about this by first thinking about a graph of alpha. So I'm working on the interval -1 to 1. and I have some partition of this interval, right? Doesn't have to be uniform, right? So maybe those are my partition points. And then I have my function here, my function alpha of x, so that's what I want to plot here. And so alpha of x, right, just looks like it's 0 over here. And then once we get to 0, it switches to the value of 1. Okay, so this is my function alpha of x. And I want to use this to think about what these delta alpha k's are. So remember, by definition, delta alpha k is just alpha of x sub k minus alpha of x sub k minus 1. So let's think about, right here, this first value in my partition, this is x0, this is x1. And so let's think about what is delta alpha 1. Well, delta alpha 1, by definition, is alpha of x sub 1 minus alpha of x sub 0. All right, what's alpha of x sub 1? Well, as I've drawn it here, that's 0. What is alpha of x sub 0? Well, as I've drawn it here, alpha of x sub 0 is 0. Okay, so delta alpha 1 is just 0. And again, that's because this function alpha does not change at all over the interval x0 to x1. And that's all that delta alpha k is measuring. It's measuring the difference between alpha at the rightmost endpoint and the leftmost endpoint. And this doesn't change over that subinterval. So that delta is 0. And you pretty quickly start to realize, well, this one will be 2. Okay, so delta alpha 2 will also be 0. Okay. Now, something interesting happens when you get to delta alpha 3, though, right? Because as I've drawn this here, if I look for this particular one, delta alpha 3 will be alpha of x sub 3 minus alpha of x sub 2. Alpha of x sub 3 is 1. Alpha of x sub 2 is 0. So delta alpha 3 will be 1. But then if you go to the next one, if you go to delta alpha 4, well, alpha of x sub 4 is 1. Alpha of x sub 3 is 1. 1 minus 1 is 0. Same thing here. So what you get for this particular partition that I've drawn is you get that all of the delta alpha k's are 0 except for one of them, and it's 1. Now, what was special about this one? Why was delta alpha k here? Why was that 1 instead of 0? Well, it's because this is the subinterval of the partition where the jump happens, right? This is the subinterval of the partition that contains 0. Okay. So I think about what's going to happen for a general partition. All of these, right? Throw in all the points you want into your partition. Most of the delta alpha k's are going to be 0, right? The only things I need to worry about are subintervals that contain 0. And so if I think about, okay, how could that happen? Well, there's actually 2 ways it could happen. One is like this, okay? So you could have that 0 is strictly inside one of the subintervals, okay? In that case, all of these will be 0 except for 1. And so this sum will end up being capital M sub I times delta alpha I for some particular value of I. And we'll specify that in a second. Okay. Now, the tricky thing that can happen is, what if 0 is actually in your partition? Okay. So if you think about that for a second, that means that you actually have 0 in both of these subintervals, because now it's in this subinterval and this subinterval. However, again, because of the way this works here, my delta alpha k on this side will be 1, because delta, like alpha here is 1 and alpha here is 0. And that difference will be 1 minus 0, which is 1. Over here, however, my alpha will be 1, my alpha will be 1, 1 minus 1 is 0. So you're still only going to get one subinterval where the delta alpha whatever is not 0. Okay, and when it's not 0, it just ends up being 1. So you always end up with this just being capital M sub I for some value of I. Now, how do we describe which I that is? Well, essentially, it's the I whose subinterval contains 0 and points to the left of 0. Okay. So we can say that this is equal to M sub I. Where 0 is in the ith subinterval, so is in x sub I minus 1 to x sub I. And I'll just keep this piece over here, and minus infinity to 0 intersect x sub I minus 1 to x sub I is not the empty set. So again, this is the subinterval. This M sub I comes from the subinterval that contains 0 and points to the left of 0. Okay, so again, if you end up with 0 being right on that borderline, you pick the one that contains points to the left of 0. All right. Now that's great. We can actually do something almost identical for the lower sums. Okay, because again, all of this has to do with the delta alpha k's. So this will be the sum k equals 1 to n of little m sub k delta alpha k. But again, all of our alpha k's are going to be 0 except for 1. Okay. And that 1 that's not 0 will just be equal to 1. So this will just be equal to little m sub I, again, where this I is just telling us which subinterval of the partition satisfies these properties. Okay, so it turns out that our upper and lower sums, they reduce quite substantially. Okay, so now that I know that, I might want to think about, okay, well, what is the, say, upper Riemann integral of f d alpha x? Well, by definition, right, this is the infimum over all partitions of the upper sums of f with respect to alpha over those partitions. All right, so let's think about this. So I know that each of these upper sums is just the maximum value of the function, right? This m sub I is defined to be the supremum of the function over this subinterval. Okay. So how do I want to look at the infimum. So I want to minimize these maximum things. These are sort of referred to in analysis as minimax problems, and they can be sort of brain teaser, sort of brain twister sort of things sometimes. So I want to figure out what the smallest possible maximum I could get out is. Well, think about this. I'm always on an interval that contains 0. Okay, that's one thing. And if I want to decrease a maximum, what I should do is I should take it over a smaller set. Now, why does that make sense? Well, think about this in terms of heights, right? If you look at the tallest student at the whole university, that person's probably fairly tall. If you look at the tallest person in the math department, that person's probably not going to be as tall as the tallest person at the university. They could be if the tallest person at the university happens to be in the math department. But, probably since you're looking over a smaller set, the tallest person is going to be a little bit shorter. And then if you look at the tallest person enrolled in Math 5610, right, that person is probably a little bit smaller. So you can decrease the maximum by taking the maximum over a smaller and smaller and smaller set. So as we think about what can happen over every possible partition, this thing will be minimized when this interval is as small as possible. Now, if I think about what happens, this interval I want to be as small as possible, right? So this interval should be as small as possible, but it has to contain 0 and points to the left of 0. So what's happening is that interval is collapsing down to 0. right? Because it has to contain 0, but I'm looking at partitions that have smaller and smaller and smaller and smaller and smaller norms, right? That those intervals are getting small. So what's going to happen here is this is going to collapse to just the single value of the function at 0. So again, visually, what's happening here, I have this function. My function looks like this. Here's 1. Okay. And I'm looking at all of these things, but they are maximum values of this function over some little interval. So since this function f is actually increasing, the maximum just occurs at the right-hand endpoint. But these intervals, sort of as to take this infimum, these intervals have to be getting smaller and smaller and smaller. In particular, this one must be getting smaller and smaller and smaller. And so what's happening is this is moving closer and closer to 0 because 0 has to remain in this interval. Okay. So we just collapse to f of 0, which is 1. Now, we can make a nearly identical argument for the lower integral. So the lower Riemann-Stieltjes integral of f of x d alpha x is the supremum over all partitions of the lower sums, the lower Darboux-Stieltjes sums. Now, if I think about these, any one of these lower sums is just the minimum of the function over some little interval containing 0. So here, that would just be like at the left endpoint. But again, these intervals, how do you now want to maximize these minimum values? The way you maximize a minimum is by taking the minimum over a smaller and smaller set. Use that same example I did before, but instead of tallest person, right? Think about shortest person. The shortest person at the university is probably shorter than the shortest person in the math department, is probably shorter than the shortest person in Math 5610, right? And so what we get here is that in order to make this minimum as large as possible, we need to make our set get smaller and smaller and smaller. When that happens, it has to contain 0. This again collapses to 0, and you just end up with the function value at 0. Okay. Which again, in this case, the function at 0 is equal to 1. And so what we end up with here, right, because these are equal, this implies that our function is Riemann-Stieltjes integrable with respect to this alpha, and its value is just, well, this is f of 0, which in this case is 1. Now, let me also point out, we really didn't use anything about this function f, right? There's sort of nothing special about this function f. The only fact we used about f that we really had to use was that f of 0 is 1. I did mention here that, the maximum and minimum occur at the left and right endpoints. That's using the fact that this is monotone increasing, but you actually don't even need to use that. So we could actually, for any function f, any function, this is just equal to f of 0. So even if we came up here and got rid of our particular definition of f, we could come up here and say, no, I don't want that. I don't like that function f. I could replace f with any function I like, and I would get that this is f of 0. So, think back to Riemann integration. We saw, for example, that the indicator function of the rationals is not Riemann integrable. It would, however, be Riemann-Stieltjes integrable with respect to this particular value of alpha. Okay. So again, we see that this is really giving us something a little bit different than the Riemann integral, but it's also a generalization of the Riemann integral. It allows us to compute different types of things. Now, if this example feels a bit confusing, you shouldn't feel like you're behind. Riemann-Stieltjes integration is, while it is a generalization, and you'd like to think, oh, I have lots of intuition for Riemann integration, it really is a pretty broad generalization, and so it actually takes quite a bit of work to gain intuition about Riemann-Stieltjes integrals. So you should not feel bad if this first time looking at it, this all feels a little opaque. Go back, think through the example again, reach out to me if you have questions. But even over a decade after having first learned about the Riemann-Stieltjes integral, I'm still gaining intuition as I teach these courses and I work through various examples. In some ways, I think this is an example of something that you maybe never fully feel comfortable with. You just get used to some of the intricacies. But again, it is a very broad generalization of the Riemann integral. And therefore, again, it does take a while to build up some intuition. Now, because, however, the definitions are fairly similar, we will be able to prove a lot of the same properties, and we'll actually be able to prove some other things about the Riemann-Stieltjes integral, which we will do in subsequent videos. We will also continue to work through examples to try and gain more intuition about the Riemann-Stieltjes integral. But hopefully this video has helped introduce you to the definition and get you at least a bit acquainted with the Riemann-Stieltjes integral.